Good morning, ma'am. I'm Kevanila. I'm from CSA Department of AML. My roll number is 259558626. And today my topic is sleep pattern classification. We can go through that. Introduction to sleep pattern classification. Sleep pattern classification involves identifying and categorizing stages of sleeping using psychological signals such as EEG, EVOG, and EMG. Accurate classification enables diagnosis of sleep disorders like insomnia, sleep apnea, and narcolepsy in clinical settings. And the traditional manual scoring by sleep technicians is time consuming and prone to inter-rater variability. And the AI-driven automated systems offer scalable, consistent, and objective alternatives to manual analysis. So this presentation explores how machine learning and signal processing techniques are applied to classify sleep stages effectively. This is the introduction to sleep pattern classification that involves identifying and categorizing stages of sleeping that using psychological signals, and the traditional manual scoring by sleep technician is time consuming. So this presentation explores how machine learning and signal processing techniques are applied to classify the sleep stages effectively. We can go through that. Sleep stages and polysomnography, the PSG. The human sleep is divided into non-REM, that N1, N2, N3, and REM stages. Each they contains the distinct brain wave patterns and physiological behaviors. Polysomnography records multiple signals during sleep, including electroencephalogram, electroculogram, and electromyogram (EMG). That the EEG electroencephalogram captures brain activity, EOG tracks eye movements, and the EMG measures the muscle tone, that key indicators for distinguished sleep stages. And the sleep technicians scored 30 seconds epochs of PSG data according to the American Academy of Sleep Medicine, that AASM guidelines. And that these labeled datasets serves as ground truth for training and evaluating AI-based classification models. Human sleep is divided into non-REM and REM and non-REM stages, that PSG, EEG, EVOG, and the EMG. The EEG captures activity like the eye movements. The EMG measures the cycle tone, indicators for distinguished sleep stages. The sleep technicians scored 30 seconds epochs of PSG data according to the American Academy of Sleep Medicine, that AASM. So these are the sleep stages and polysomnography. And next, the signal acquisition and pre-processing. The raw PSG signals are often contaminated with noise from muscle artifacts and the line interference or electrode movement. And the pre-processing includes filtering. Examples, the bandpass is 0.5 to 30 Hz of EEG, that artifact removal and normalization to improve signal quality. And the common techniques include independent component analysis (ICA), that is to isolate and remove eye blink or muscle artifacts. The signals are segmented into fixed length epochs, typically 30 seconds, to align with the clinical scoring standards. The proper pre-processing ensures that features extracted for classification are reliable and representative for true neural activity. The PSG signals are often contaminated that with noise from muscle artifacts, and the pre-processing that includes the bandpass, that is 0.5 to 30 Hz of EEG, and the ICA is used to isolate and remove eye blink or muscle artifact, and the signals are segmented into fixed length epochs, that is typically 30 seconds. And the proper pre-processing ensures that features extracted for classification are relieved. These are the signal acquisition and pre-processing. And next, feature extraction from sleep signals. The time domain features include mean, amplitude, variance, and the Hijroth parameters that describe signal activity, mobility, and complexity. Frequency domain features like power spectral density, the PSD, that reveal the dominant brain rhythms such as delta, theta, alpha, and beta waves. The time frequency methods such as short time Fourier transform, the STFT, or the wavelet transform capture how frequency content evolves over time. The nonlinear features like entropy and fractal dimension help quantify the complexity and predictability of EEG dynamics. And these are the time domain features that includes the frequency, mean amplitude, variance, the Hijroth parameters, and that which describe the activity of the signals and the mobility and complexity of the signals. And the time frequency methods such as STFT or wavelet transform capture how frequency contents evolves over time. And the feature selection techniques reduce dimensionality and retain only the most discriminative attributes of classification. These are the feature extraction from sleep signals. And next, traditional machine learning approaches. We can go through the approaches that classical models such as support vector machines, SVM, and random forest k-nearest neighbors, that KNN, have been used for sleep stage classification. These models require handcrafted features and perform well on smaller, well-curated datasets with clear stage boundaries. The SVMs find optimal hyperplanes to separate different sleep stages in high-dimensional feature spaces, and the random forest combine multiple decision trees to improve accuracy and reduce overfitting through ensemble averaging. Despite good interpretability, traditional methods struggle with complex nonlinear patterns in raw physiological signals. These are the traditional machine learning approaches that these models require handcrafted features and perform well on smaller datasets, and the SVMs find optimal hyperplanes, and it is used to separate the different sleep stages in high dimensional feature spaces. And the random forest combines multiple dimensions trees to improve the accuracy, and despite good interpretability, and the traditional methods struggle with the complex patterns in raw psychological signals. And next, deep learning for sleep stage classification. Deep learning models automatically learn hierarchical representations from the minimally processed PSG signals. The convolutional neural networks detect local patterns in EEG spectrograms or time series data across different scales. The recurrent neural networks, the RNNs, that especially long short-term memory units that use it to model temporal dependencies across consecutive sleep echoes, and the hybrid architectures like CNNS, LSTM, that combines spatial feature extraction with the sequence modeling for improved performance, and the end-to-end training allows the model to optimize both feature learning and classification jointly, reducing reliance on manual engineering. This is the deep learning for the sleep stage classification. And next, common deep learning architectures. The EEG-NET is a compact CNN designed specifically for the EEG-based tasks, using the depthwise and separable convolutions to reduce parameters. SleepNet integrates CNN and RNN layers to capture both the local spectral features and long-range temporal dynamics in sleep data. Attention mechanisms allow models to focus on the most informative time segments or frequency bands during the classification. Autoencoders can be used for unsupervised pre-training or anomaly detection in sleep recordings with limited labels. And the transfer learning enables leveraging models trained on large public datasets to improve performance on smaller domain-specific data. This is the common deep learning architectures that SleepNet integrates with the CNN and RNN layers to capture both local spectral features. And the autoencoders can be used for unsupervised pre-training. And the attention mechanisms allow model to focus on the most informative time. And the transfer learning enables leveraging models trained on large public data sets. And the public data sets for training and evaluation are that the sleep EDF dataset contains overnight PSG recordings from health and is widely used for benchmarking sleep classification models. The ISRUC sleep dataset includes data from both healthy individuals and patients with sleep disorders, offering clinical relevance. These datasets are typically split into training, validation, and test sets to ensure fair evaluation of model performance. And the standardized benchmarks allow researchers to compare different algorithms under consistent conditions. These are the public datasets for training and evaluation. Next, performance metrics and evaluation. The accuracy measures the overall proportion of correctly classified sleep epoch across all stages, and the Cohen's kappa evaluates agreement between model predictions and human annotations, accounting for chance agreement. And the confusion matrices reveal which stages are frequently misclassified, such as N1 often being confused with wake or N2. The cross-validation and subject-independent testing help that it can ensure generalization across unseen individuals. This is the performance metrics and evaluation. And next, challenges in sleep pattern classifications are the class imbalance is common with light sleep N2 dominating and deep sleep or N1 being underrepresented in recordings. Noise and artifacts in real-world home-based recordings reduce signal quality compared to controlled lab environments. The label noise arises from consistencies in manual scoring by different sleep experts. The real-time deployment requires models to be lightweight and efficient, posing challenges for complex deep learning architectures. And the applications and clinical impact are the automated sleep staging supports large-scale sleep studies and enables population-level analysis of sleep health trends. And the wearable devices with embedded AI can monitor sleep quality at home, promoting preventive healthcare and lifestyle adjustments. And the integration with electronic health records allow longitudinal tracking of sleep changes in patients with chronic conditions. These are the applications and clinical impact of sleep. And next, ethical considerations and limitations. Patient privacy must be protected when handling sensitive psychological data requiring secure storage and transmission protocols. Bias in training data may lead to reduced accuracy for underrepresented demographic groups such as elderly or pediatric patients. And the regulatory approval is necessary for clinical deployment, requiring rigorous validation and transparency. And the explainability remains a challenge as deep learning models often act as black boxes, limiting trust in medical decision making. These are the limitations. And the future directions and the research trends are multimodal learning combines EEG with other signals like heart rate, respiration to improve classification robustness. And the federated learning enables model training across multiple hospitals without sharing raw patient data, preserving privacy. Integration with generative models may help simulate rare sleep events or augment small datasets for better generalizations. And these are the future directions and research trends. Thank you, ma'am.